Is now to go from space back to Earth and try to use drones, so autonomous flying vehicles for power generation. So this is the second part. So the outline here is, thank you very much. So the outline is that first I will introduce the source here and motivate why it is a good idea to harvest high altitude winds and produce energy from them. The technological part will come in the second part here. This is about the technology which is called airborne wind energy. And in the third part, I want to show how you can build a wind drone for low cost for yourself and experiment with this kind of technology. So let's start with the first part. And here, as a reminder, is the conventional energy supplier wish list. So probably what your global players in conventional energy would think about it or tell you. They would say that it's a surely clean enough resource, and meaning on timescales here, it is exploitable of the order of 1 human life expectancy. It's controllable, especially economically and politically. It is depreciable economically and leads so to a very high profit for some players. Unfortunately, there's also the technological part, and here sometimes it's driven by hope, saying it will be okay. But as we know, it might be mostly harmless. So as we see here, for instance, there are catastrophes like Chernobyl. This is after the catastrophe, where you have the memorial for the people who died. Then you have scenarios during the catastrophe here. This is Deepwater Horizon being like desperately tried to extinguish the fire by the US Coast Guard and fire brigades. And of course, what I don't have to mention here, but in times of fake news, is important to mention, we are before the catastrophe. So this is here a plot of the carbon dioxide concentration in the atmosphere taken from ice. And as you see here, the ice ages give this variations over 500,000 years. And now we are at this spot here that points up. And if you resolve this into the time scale, extend this time scale from the last 1,000 to 2,000 years here. So we are here at this spot at 2000, year 2000. Then you see that this rise has started at the industrialization. So it's a clear sign that we have to do something, and we have to do it quickly. Yeah, so now let's try to propose something which can be part of the solution, namely sustainable energies. And here's a wish list of what probably you would think it should be. It should be sustainable, ubiquitous, continuous, accessible, and profitable at the very end. So does such a source exist? And first I should define what it means. So sustainable means it should serve present needs without compromising the future. And this is clearly not what we are doing now. So it should be available on time scales which are like the lifetime of our central star, if possible. It should be ubiquitous, meaning that it should be present almost on any location on Earth, so that we can, without a very complicated long-range infrastructure, have access to the energy. It should be continuous, meaning it should be present at almost any daytime and seasons, so that we can plan of what we produce. And of course, it should be accessible, meaning it can be tapped by the technology and lead to a significant contribution to our energy mix. And profitable should, of course, also be. So does it exist? And the answer is yes, and I want to show that this airborne wind energy can be a big part of it. So here I have a table of some sustainable energy sources, and the wish list items are written here, and I put some of the sustainable sources. So there is fusion, there is solar energy, terrestrial, and also the spatial energy of which was presented by Anya and by Stefan before, hydro energy, geothermal energy, and conventional wind energy. Where by conventional wind energy, I mean wind energy up to approximately 100 meters, which is the hub height of wind turbines, approximately. And as you can see, some of these items here are not fulfilled by all these different approaches. So for example, the spatial energy is clearly not ubiquitous because you have this beam, as we heard, which is just like basically hitting a certain spot on the Earth and they're transferred into energy, so you have to distribute this energy. Also, it is not yet accessible. On the other hand, wind energy here, conventional wind energy, is not ubiquitous because you can only select certain spots, and it is not continuous because you cannot really plan when the wind is blowing and when it's not blowing. So let's add to this list what is called high altitude wind. And high altitude wind is clearly sustainable because it's also wind energy, so it's like driven as all the other wind energy as well. And high altitude means to go to heights which are above 200 meters and try to drain energy from these winds. So let me argue why it is a ubiquitous source. And for this, Philip, who is also here and part of the team, I'm very happy he has made this very nice plot here, which shows the western part of Europe, and it shows the ratio of wind power which you can extract at an optimal height, which should be below the 1,000 meters. So this is just an arbitrary, at the moment, limit to say that we can have a system which can basically get up to 1,000-meter height, and compare it to this wind energy, which is basically available at 100 meter. And in this plot, you can see at the coastline, there is a line here, and this line is the line where in the interior you have already a doubling of the wind power. So meaning at the coastline itself, if you go to higher altitude, you have the double wind power available than at 100 meter. Even better, directly at the coastline, there is another line, which is a factor of 4 better. So as soon as you put your wind turbines on land side, you will be a factor of 4, you have access to a factor of 4 higher wind power. And here in the region slightly south of Leipzig, there is another line. This is a factor of 8, where you become better in wind power, in high altitude wind power. So seeing that the coastal regions have already a factor of 4 in this ratio better, and the inland between 4 and 8, there are the signs, sorry, they should be reversed, of course. So saying that here, the sites of conventional wind energy harvesting, which are now very limited, and where you put, for instance, all the wind turbines in the north, they become much more accessible if you go to higher heights, because there you can basically use all the land sites. So this is you have more sites available when you harvest at optimal height. And here, as an example about why it is a continuous source, you see a time distribution of the wind velocity in January 2016 in Leipzig. The wind velocity is here increasing from yellow to red, and the altitude is displayed here, and this is the time scale of the month. And what you can see is at 100-meter height, you have almost like only in the lower parts you have winds. Whereas if you go to higher heights, you have the reddish parts where you have high wind velocities. So this shows that continuity is already improved if you go to higher altitude, especially for land sites. And this is almost impossible for conventional wind turbines. You would have to build the mast higher and much, much bigger structures. And also what is displayed here is the optimal harvesting height. So this is the height, again, below 1,000 meters, where it would be optimal to harvest wind at a certain time, displayed over the whole month. And if one goes from this plot to the histograms, to the time distribution of the different wind velocities, you get this picture here. So this is the spots, the histograms of 100, 170, 500, 1,000 meter, and of the optimal height, so if you adjust your height. And one of the things that you can see is that the mean is clearly shifted to higher wind velocities if you increase the height. And also, if you harvest at optimal altitude, you shift the whole probability distribution to the right. So and what increases there is that the fraction of time below 5 meters per second, which is like the time where the cut in wind speed for your wind turbine. So you would like starting produce energy, the probability to have such winds is increased from 76% to 87%, which is quite a lot of increase. So adjusting to varying optimal harvesting height is not only almost, but is really impossible for conventional wind turbines. So one has to find another technology which is better and can give you access to these high altitude winds. So this is the plot again from before. So I have now a little bit motivated why the source is ubiquitous and continuous. Now the question is it accessible and how it is accessible? And this is the technological part, which is called airborne wind energy. So how do we access these high altitude winds? So and for these, let's come back to the design challenges, which would be necessary to go to high height. So high altitude means that you cannot just increase your tower and have more torque on your foundation and just scale up the system. So you should avoid proliferation of mass and proliferation of the tower and foundation. And also varying altitude means you shouldn't have passive stabilizing static structures, but find something which can vary. So just as an example here, this is the sky walk in the Grand Canyon, and this is already a quite scary lever arm which you have. And if in comparison you take your modern wind turbine, you rotate it by 90 degrees and compare it in size to this, you can see what kind of torque will be will act on the foundation. So this is already a very big piece of technology you have here. So we have to do better. And this is the second part, namely airborne wind energy, so the technology itself. So the first slide is probably the most important of this part because it explains the idea behind this technology. So you take autonomous drones, which are at most flexible, connected to the ground via tethers, and extract wind energy via these drones. So how does it work? So look at this conventional wind turbine here. You have most of the energy is produced by the outer part of the wings. They are rotating with the highest velocity, and at the same time you have the largest lever arm. So you produce most of the energy in the outer part. The inner part is more or less passive stabilizing structure. So you remove that structure and replace it by something which is flexible, and the first which comes to mind probably is a tether, with which you attach it to the ground. And then you have just the active part here, which is now an aircraft moving in this circle, which before was circulated by the wingtips to extract your energy. This is the principle. So how do we bring down the power when circulating this aircraft? So we have to, in some way, transform it to electric power. So there are, which are not shown in the picture before, lighter than air systems. So you just basically take a balloon, you put your wind turbine at high altitude and extract the power. And here the tether can clearly serve as the power line. But what we can also do is crosswind flight, which was shown in the picture before. So here you have a moving aircraft which can move in something which is called the drag mode, meaning that you have onboard generators on the aircraft. So essentially it's a propeller aircraft, but the propellers are reversed in repeller mode so that the repellers produce energy for you. And then the tether serves as power line. So this is the principle is shown here. So here you can see the generators, and then the power is brought down by the tether. And the second part, strategy is using the so-called lift mode. So here you have ground-based generators, and the tether itself transmits the power. There are no power lines in the tether. So here you use that the power is given by the pulling force times the real out velocity of the tether. So you circulate in some patterns with your aircraft, and you lose the lift force acting on the aircraft to unreel this tether from a drum. And at the drum on the base station, there's a generator attached, which helps you to get the energy, to transform the energy into electrical energy. And of course, at some point, the tether is maximally reeled out, and then you have to go to a reel-in phase, where with minimal energy, you reel in the tether again and start periodically this phase again. So these are the concepts, and there is a whole zoo of airborne wind energy devices and proposals which show that this technology is still in a very early stage of being developed. So you have people here flying figure-of-8 patterns with the aircraft. So some things are lighter than air turbines, which look very exotic, like this one. Probably this one you have seen in media already. Proposals like this here. There are quadcopters which produce the energy by rotating of their propellers here, and all kind of exotic lever arm and aircrafts which you can use. So let's bring a little bit of more order into the technology, into the proposals. And one of the things I want to discuss, which is very promising, is what is called crosswind flight. So here, as an example, is a comparison of a conventional lighter than air system with the big wheel in London. So this is one of the biggest wind turbines. And the harvesting area is, so the effective area of such a wind turbine is the swept area of your propellers, essentially. So now let's look what happens if you move an aircraft instead through the wind. Then the picture of before is like of that size. And if you take an aircraft which is the same wing area as the wing areas of the propeller here, your harvesting area is of that size. It's much bigger. And the reason for this is that the effective area is now given by the wing area times coefficient, which is the square fraction of the lift to drag coefficient of the aircraft times the lift coefficient itself. And this factor is of the order of 200. So it gives you, it increases the efficiency of your wings dramatically. This was already found by Light in 1980. And you can now ask, why does it take 30 years from this idea to first systems? And the answer is, in this community, probably very interesting, is why are these prototypes appearing only 30 years later? It's because sufficient computer power, so for the control algorithms, which allow you to control such flight modes, was not available. So as an example, here's an illustration of one of the current leaders in the field called Ampix Power, showing a crosswind airborne wind energy system versus a conventional system. So here's the conventional wind turbine for 2 megawatts. And the conventional, this is the conventional system, and the airborne wind system is, this is the ground station, and this is the aircraft. So one of the things which are visible in this picture is that it has much less like even side impact in the environment. So having something like this is much less disturbing from the, even from the aesthetic point of view than this huge wind turbine. So now the next step would be to look closer to the technology and see what are the AVE system components that you need to build such a device. So first of all, there is the drone or the fixed-wing aircraft. We have seen that it's very good to have large lift and small drag coefficients, so you need something which is like a rigid glider, more or less. On board, you need sensors like accelerometer, gyroscope, GPS receiver, barometer, and a pitot tube to measure the airspeed. And this is to determine the system state. That then is like reacted on by the control surfaces of in the case of an aircraft, by ailerons, flaps, and the rudder. Moreover, you need, of course, a microcontroller and algorithms which do the state estimation. So from the sensor data, they compute the state of the system, meaning this position, attitude, velocity, and you have to navigate. So, and of course, you might need something like a propeller for takeoff, landing, and energy generation in case of drag mode. The second thing is, of course, the ground station. So here you need the drum for tether wind-up. You need a motor, which eventually has to be transformed into generator mode if you have the lift mode. You need power converters, also microcontrollers and algorithms which synchronize your ground station operation with the drone, and you need a runway catapult or something alike for takeoff and landing. So far it looks quite simple, but the devil is in the detail. And here I found a nice quote a colleague of mine, Giovanni Litrica, has done in one of his talks. And I liked it very much because it displays very well what challenges have to be still overcome. So it starts with theory is where nothing works, but everyone knows why. And to demonstrate this, let's have a look at this video here, which is one of the flight attempts of one of the companies. So the aircraft lifts off. There's no sound. Yet, no, there's sound. Yeah, and the desperation of the founder was clearly hearable at the end, and you could see that the tether ruptured. And then there was no way to recover that mode, so the aircraft was lost. Second, sometimes practices when everything works, but no one knows why. So there are also positive surprises. And here is a launch, a catapult launch for an aircraft which now uses weight. So, So a positive surprise for a test. And finally, sometimes if you combine theory and practice, then nothing works, but no one knows why. This is where the complication really is. The devil is in the detail. And here you can see a video from a flight, which is crosswind flight. Everything seems normal. And then the prototype is again lost. So this is complicated. But there is a lot of progress, and so I want to come closely, very quickly introduce the current industrial status. So I focus on 3 companies which work on that. So one of them is Enerkite in Berlin, and they have now a system which is basically stationed on such a truck, and this is a crosswind system of a passive wing, so it's steered via 3 tethers, and it produces up to 30 kilowatts of energy. Then you have Ampix Power. They have here the launching site in the Netherlands, and they are currently producing this aircraft here, this type, which in crosswind is a crosswind system in lift mode, and at the end will produce up to 250 kilowatts of power. This is under construction. And finally, there is Google X Makani in California, and they have built a drag mode aircraft here, which is flying, and I can show you a video that they have on their homepage very nicely, where they show a flight, so that you can see that this 600 kilowatt system is working. Here you see the onboard propellers. You can see the tether down here. This is from the tether attachment point. Yeah. So the things are working. There are prototypes. Yeah. But one of the things which are important is one has to test, and get experience from tests. So experience is what you get when you're expecting something else, really. So what does it mean? So we have to test, analyze, adapt the systems. So because many, as you could see from this design variations in the zoo, which I've shown, many of the concepts are still open. So for example, the design of the airframe, if you use a biplane, a flying wing, or anything alike, or something totally different, is still open. The tether construction, what kind of materials to use, is still open. The materials in itself is still open for the aircraft, etc., etc. The mode of operation, that means takeoff, landing, and drag versus lift mode, is still an open question. What is the best thing to realize in for industrial products? And then control hardware and software and algorithms have to be tested thoroughly, of course, and have to be certified by the aerospace agencies, of course. You want to have it fail-safe. So what you have to do is you want to have total losses in experiment. You want to do the experiment which will lead to a total loss of your system. So here comes the idea that instead you should build a cheap and disposable test platform instead of a largely scaled up system first, before you build the expensive prototype and do tests on them. And this brought us to the idea to provide a low-cost open source test platform where everybody at home can build his own wind drone. And this is the third part of the talk, so the do-it-yourself wind drone. What are the ingredients here? So first you need a drone. So here I want to show the airframe and reinforcement hack, which is necessary to prepare your airframe for the additional forces by adding the tether. Then there's a ground station, and here I want to motivate why the drone is essentially behaving like a fish, in this case a barracuda. The next thing is navigation on curved manifold is very important because you have like a constraint coming from the tether. And finally, you need something for your for control, which is the autopilot. So in this case, it's the autopilot open source project which we adapted. So let's come to the airframe reinforcement hack. So what you use, take your favorite polystyrene airframe. So in this case, it's an Easy Star 2. And glue the wings together. This is the lower side of the wings. You put in there a carbon rod here in this part, and you stabilize it with racks which you glue into the slits we can see here. And then you wrap carbon in the forward part of it where most of the aerodynamic force is attached. Then you have the carbon rod where you can wind around your tether, and you install additional tubes for fixing the wings on the fuselage. So the fuselage is here. We cut off the engine blocks, included additional carbon rods, so you can put these carbon rods on these carbon rods here and fix everything with screws. So to show you how that looks like and what the size of this model is. So here is the original size aircraft. With carbon, and you can later, if you want, pass by the assembly area and look at it and have a look at it and touch it. So this is how it looks decomposed into different components. So again, wings and so on and so on. The servos for the control surfaces. The central unit here is the Pixhawk autopilot. So the microcontroller, which contains some of the sensors. You have a GPS sensor. In addition, you have a telemetry antenna for data transfer to the ground station, and you have RC control for manual control when you switch out of auto mode to have manual control in emergency situations, or if you want to make other kind of flight tests. Yeah, so now this is the drone itself. So now it's the question what to do with the ground station. And here let's look why the drone behaves as a fish. Because what it does is, like in fishing, you would need a free-moving tether. It has to be fast and fail-safe, reeled in and reeled out. And it should remain twist-free so that it doesn't give any knots if it is not under tension. And the thing which we came up with, which best serves for our needs at the moment, is an offshore fishing reel. So you need offshore here because the drum has to be perpendicular to the rod. This guarantees you that the reel out phase is twist free on the tether. Other fishing rods have the drum aligned with the rod, and then you accumulate twist on the tether, which is can lead to knots, and then it's not a good idea. It's destroying your tether. So, and this is the first flight test. So we were very enthusiastic and started the first flight test. And here it is.
Jetzt habe ich Hutzug. Hinterher. Ach, ja. Versuch mal rauszugehen. Manual. Achtung, Achtung, versuch ihn zu fangen. Na gut.
Okay. So, unfortunately, it did not work. So what happened, this was the result. The tail was broken, and because the tether apparently wrapped around the back of the aircraft, and then it became uncontrollable. So we came up with, what do we do? If you don't know any better, use carbon. So we put some carbon on the lower part of the fuselage to reinforce it. Yeah, and then, of course, you have to think about writing your navigation code to navigate if you are under tethered flight. So here is the recipe for how to do it. So first you take one Git clone of Autopilot, this open source software. You take one curved two-dimensional manifold, which is essentially given as a hypersurface embedded in three-dimensional Euclidean space. In case of constant tether length, this is just a hemisphere S2, which is centered around your ground station. Then you take a planar curve, which you want to fly along, or curve segments, and a pinch of differential geometry to wrap it on the sphere to make this curve appearing on the sphere. You take a little bit of classical mechanics for the flight control to transfer the curve accelerations into actually control surface motions. And then you need, of course, a dozen coffee for doing so. You put everything together into, of course not the coffee, into the computer algebra system and steer well, and let the CPU bake it at 100 degrees, and then you come up with a smooth, at least C1 curve. So the curve is shown here. So this is one part of a figure 8 pattern. So the other part would be behind here. It's composed of 2 geodesic segments and 1 turning segment, and they are C1 glued together here. And these are the equations, so you can find in the paper. I don't want to go into detail. So now you have to modify the source code of this autopilot project. So here they are highlighted the patterns which you basically have to, where you have to do modifications. You have to implement new flight modes and change some of the control algorithms, and then you come up with the next flight test. And here is the next attempt.
Ausstellen müssen wir mal sehen, ob die dann verschieben müssen. Ja.
Ja. So. Yeah, the whistling sound you have heard at the end is the tether being dragged through the air. So there was really tension on the tether. And you can also see this if you do a data analysis on the flight data later. So here's, for example, multiple possibilities. You have a lot of data which is possible to analyze. So the autopilot, this was very nicely done in this open source project. So they have a data file with all primary and secondary data you can use for your analysis. So for instance, this is the flight curve with different flight modes which we used. You have the attitude of the aircraft. You can look to deviations in radial and transverse directions. You can look to tether tension, or like a measure for tether tension by looking to the length variation of the tether. And you can, of course, do time series analysis of how your figure 8 pattern is flown along. And yeah, that is what you can do with this very nice autopilot open source software, which is available, written by many people on the internet. So the question which remains is, after all of this, will it be fail-safe to 100%? And the answer is nope, it will not. There will be, of course, accidents happen, but the thing is, nothing is fail-safe. And so here's a standard wind turbine. And look for yourself. You see, there is no 100% guarantee, but we have to try very hard to get it as fail-safe as possible. So yeah, this is essentially it. That was the talk. So what I want to say is that the current status of airborne wind energy can be seen here by a nice book in the on the Springer page, which you can download here. And we are very happy to have any kind of critical remarks, input, help in developing the system further. So please, if you want, look to this webpage. There's a lot of information, including a paper, and we'll be very happy for any kind of help. And yeah, and finally, I would again stress that we could rely on this tremendous work of the open source community working on this autopilot project that has helped us to realize this project in a very short time. So very happy about this. And I want to thank, of course, Philipp Bechtle, who is here, and Thomas Germann and Maximilian Schulz-Herberg, the students, and Udo Zillmann, who cannot be here, for working on this project and putting so much work also into it. Thank you very much for your attention.
Great. And we take 2 more questions. microphone here and here, 1 and 5. So 2 questions. The first one, please.
So you talked a lot about about controlled flight. How does it compare energy-wise to uncontrolled flight? Basically putting a propeller on a kite.
So the thing is, a propeller on the kite, with kite you mean, I guess, non-rigid structures. So meaning that the first question is, how do you want to put a propeller on a kite if it's non-rigid? So that is a question which goes back to you. So because that is something is not clear to me. But in any case, a rigid airframe is harder to control than a kite. So there are people who work with a kite, and by kite surfing, or if you do steer normal kites from the ground, it's like moving not that fast in the wind field, so it's easier to control. This is a big benefit of kites, and also the weight is a big benefit. But the power output, because of the worse lift-to-drag coefficient, is unfortunately not that efficient as a rigid aircraft. So you want to go to a rigid aircraft.
If you leave the room now, please be quiet, because we have questions and answers here. Number 3, please, and that is the last question, I'm afraid, but you can ask questions after the talk.
I want to go back to the space part. I was wondering, there are some ideas about bootstrapping like a solar station on the moon, and then like shipping, I don't know, hydrogen or like pre-charged lithium batteries back to Earth and back and forth. Is it like realistic or not really?
I think also this approach would be quite expensive, and you have to install this infrastructure on the moon first, and you have to establish the flight bases back and forward. Yeah, realistic is a thing, At the end, it's a question of money and investment. And I'm not sure whether this would pay out, but we haven't analyzed this kind of approaches yet.
Thank you. So thank you very, very much, Stefan, Anja, and Christoph. Give them a warm applause again, please.
Thank you.